The Gram-Schmidt orthogonalization process is a way for us to convert a basis into an orthogonal basis. Now, this process is useful because then we can really make use of projections, but it's got another way more important application. Now, this is a little bit more advanced. In real life, when people want to use linear algebra, like within Google, within graphics processing, all of it has to be done and implemented on a computer with numerical computer algorithms. Now, there's a whole host of problems that arise when you start doing that. There are all interesting types of errors that don't have anything to do with linear algebra per se, but with the implementation into a computer program. So it will turn out that using orthonormal bases has a real advantage to when we start implementing these numerical routines. So I want to show you a matrix factorization that's kind of based on using Gram-Schmidt. That is one of the backbones of a lot of numerical routines going forward in the future. We won't use too many of these in this course, but this is the right opportunity to show you what this thing is, because one day you may see it, and we want you to have been exposed to this idea. So enough about that. Let's say that I give you a matrix and it has linearly independent columns. Now, what we're going to be doing is talking about the column space. So if your matrix has a bunch of columns that are dependent, you can just basically throw them out and create a new matrix that has strictly independent columns. Those columns will form a basis for your column space. Okay? As we saw before, the Gram-Schmidt process can take those basis vectors, which are not orthogonal, and then turn them into an orthogonal basis, so W1 up to Wn, and then we can normalize them, make them all unit length, so that we have an orthonormal basis. Why do we care about orthonormal bases? Because when you have an orthonormal basis, the Fourier representation becomes really nice. You can then represent your columns in terms of this basis. There's always a basis representation, and it's always very easy to see here, right? It'll be A1 dotted with U1. Because each of these basis vectors has a length of 1, the UI dotted with UI in the denominator here will always be 1. So this formula becomes very simple, very nice and easy to use, very simple to work with. And the advantage goes beyond that. It actually will turn out that we can use matrix representations to deal with all of these things. So once I go from here, I'm hoping that you can remember that this is how the basis representation works. This is one of the key takeaways of orthogonality. There are nice, wonderful formulas for getting basis representations. Now, we're going to put this all together in matrix form. We're going to define a matrix Q that basically takes all of those basis vectors and puts them in as columns. This matrix isn't necessarily square. Now, at the beginning here, I never told you what the dimensions of A were, but let's say that each one of these vectors here, the column vectors, lives in Rm. So then the dimensions of the matrix A are m by n. So it's not a square matrix. And because that's not square, the dimensions of Q are not square either. So just because this is a matrix with orthonormal columns, we don't get to call it an orthogonal matrix. It's not square. So again, that's worth noting. It's not square. It's just a matrix with orthonormal columns. Why do I make a point of that? Because there's going to be a nice property of that later. And I realize that a lot of this stuff, the notation and the language and the terminology gets a bit confusing. And that's unfortunately part of learning linear algebra. Now, if I consider the transpose, it's an m by m matrix. Why do I want to bring in all of this machinery? Because the first thing that I'm going to do is try to remember that it's possible for me to write all of these coefficients in a nice form to do with the matrix transpose. Remember that if I were to take the matrix transpose and multiply it by any one of those columns, it would be this ui, u1 all the way down to un as row vectors, ai, and we get a column of dot products. u1 dotted with ai, u2 dotted with ai, all the way down to un dotted with ai. We talked about this before, but that's possible for us to write that way. And then at the end of the day, what you will find is that I can take any vector and then write it as this matrix product. Q times the result that I just got. u1.ai, u2.ai, all the way down to un dotted with ai. Because by definition of a matrix times a vector, I'm just taking the columns of Q and then weighting it by each one of these entries there. And just to be really explicit about it, this first weight will attach to that first column. And you can see that the order of a dot product doesn't matter. So I get the basis representation that I started with above. So what? Who cares? Now, the point of the story is that we can rewrite the original matrix A, which has these columns, in terms of this representation above. So it's going to be Q transpose AI, or A1, sorry, Q transpose A2, all the way down to Q transpose AN. By definition of a matrix matrix product, if there's a Q in front of all of these, that Q gets to go out front, and then I'll have QT A1, QT A2 as the second column, all the way down to QT AN. Okay, this matrix I'm going to call R. Now this matrix R has a special structure. What is it? Okay, let's just study it one vector at a time. This first column, QT_A1, is filled with dot products. U1, U2.A2, all the way down to UN dotted with AN. Or sorry, U2, all of these are ones, my mistake. Now remember, I know it's getting hard to remember all of the naming that we have been doing, but from Gram-Schmidt process, the first A1 is what U1 is, right? It's just some scalar multiple of it. And that means that Gram-Schmidt creates a orthogonal basis. So U1 dotted with U2 is going to be kind of like saying A1 dotted with U2. It's going to be 0. And all of these other dot products are always going to be 0. So all of these entries here are going to be 0. Because the whole important idea here is that A1 is orthogonal to all of those other vectors. You pick A1 to be the vector, that's the first one in your orthogonal basis. It doesn't matter if it has the same length or not, its direction is important. So what's going to happen here is that we will get zeros everywhere down there. Now the same exact pattern is going to happen when we talk about Q transpose A2. We will get U1 dotted with A2, U2 dotted with A2, U3 dotted with A2, all the way down the line, UN dotted with A2. These two are going to be non-zero in general. But these are going to be a little bit different. Remember that if I have the Gram-Schmidt process, if I talk about the Gram-Schmidt process, I take my W1 and I take my W2, and they are just some version of my original vectors, and they all live in the same plane. They all span the same plane. But as soon as I have a third vector, u3, and all of the rest, they are orthogonal to these. And so what you're going to find is that all of these vectors from there below, the u3 all the way down to the un, they are all orthogonal to this plane by design. That's what Gram-Schmidt does. It creates a bunch of vectors that are orthogonal. So all of these dot products underneath are going to be 0. And in general, you're going to find that R will have this structure. You're going to find that R, that matrix there, U1, A1, and a bunch of zeros there, you're going to find that this will be U1 dotted with A2 in the second column, U2 dotted with A2, and then a bunch of zeros. And that diagonal is going to continue. UN dotted with AN, U1 dotted with AN, and this is going to be an upper triangular matrix. You will have that wonderful triangle shape and a bunch of zeros otherwise. So what is the point of all of this? You can take your original matrix A, which is m by n. It has linearly independent columns. You can write it as a factorization. There's a matrix Q that's also m by n. It has the orthonormal basis. And then you multiply it by this upper triangular matrix R. Now, in order to make all of the dimensions work, this matrix has to be square and n by n, and it is upper triangular. This is what's called the QR factorization of a matrix A. You might think, oh, it's a bunch of work for nothing, right? It's so much work. And it is a lot of work, and it's very new. But the idea is that it is a foundational representation. Without it, a lot of numerical implementations of linear algebra just don't work. There are too many numerical errors that pop up to make any of the algorithms of use. Now, another way of writing this kind of stuff is by thinking, look, I could write this matrix product as QR1, QR2, etc., etc., etc. This has to be equivalent to the first vector in A all the way down to the last vector in A. That's another way of writing these things, right? And why is that important? So the columns of R hold the weights of the orthogonal or the orthonormal basis representation for each A1 through to AN. Huh? Okay, so let's take a look at that example that we worked on. In the previous video, I gave you a matrix. I showed you that this matrix has 3 independent columns. We figured out by using Gram-Schmidt that there is an orthogonal basis and there's an orthonormal basis. The orthonormal basis, each vector had a length of 1/12, 1 over root 12, sorry. And so I can construct the matrix Q just like this. So with the scaling, this would be the vector U1, U2, and U3. Now, U1, U2, U3 are an orthonormal basis for the column space of A. And if I wanted to, I could write down all of these things. I could calculate the matrix factorization. There's a special property of Q. If I were to take Q and take its transpose, I would find something interesting would happen. If I were to go Q transpose times Q, U1 row vector all the way down to UN row vector, U1 all the way down to UN, this is going to create an M by N matrix here, an M by M matrix there. So this would be N by N. It would be U1 dotted with U1, U1 dotted with U2, all the way down to U1 dotted with UN, UN dotted with U1, all the way down to UN dotted with UN. Because this is an orthonormal basis, each one of these diagonal entries will be 1. Because this is an orthonormal basis, each one of these off-diagonal entries will be 0. So there's this special property of a matrix with orthonormal columns. It has to satisfy this property, that it equals the identity. So what? Okay, if I have a matrix and I know that it has a QR factorization, I could do this lovely thing. I could left multiply it by the transpose. There's a wonderful matrix property that says you can switch the order of the brackets. I just showed you that that's I. So you could find R very simply by going Q transpose times A. So R would be Q transpose, so 1/12, and I'm going to take that Q matrix, transpose it, so take its columns and turn it into its rows. This is a 3 by 4 matrix. I'm going to multiply it by A. This is a 4 by 3 matrix, and then I'm going to end up with the following matrix. I'm going to end up with an R. Now, if you want to do this by hand, it's going to take a lot of work. You can always keep this factor of 1√12 out front. You can learn to use Sage or Octave to calculate this, but at the end of the day, you're going to get this matrix. 12, negative 36, 6, 0, 0, 12, 0, 20, 12. This is R1, R2, R3. It's upper triangular, like it has to be, and its columns. What does R1 represent? R1 represents the weights of U1, U2, U3 that have to make A1. So what this is saying is that A1 is 12 over root 12 U1, which is not a surprise because that's how we defined it by Graham-Schmidt. A2 is going to be 1 over root 12 negative 36 U1 plus 12 U2. And A3 is going to be 1 over root 12, 6 U1, 20 U2, 12 U3. There are some other calculational things that we're going to do with this QR factorization, but what's important is that you understand the underlying things that make it work. The orthonormality, the structure of the matrix products, that this thing exists. And once you know it exists, it'll make your life better in the future.